Start learning about related rates, and I really enjoy related rates because it's a very practical application of calculus. And before we begin, I want to review implicit differentiation. Probably just because it's been a little while. I'm not going to go all the way through this problem, but I just want to review our concept here that if I have something like y to the fourth plus 3y minus 4x cubed equals 5x plus 1, that is an expression that's got y's and x's in it, and we said that if I want to find the derivative of this using implicit differentiation, I do things normally, but when I do the derivative of a y term, this would be 4y to the third, I have to use the chain rule and say that that is times dy dx. That's what we learned about implicit differentiation. Plus, the derivative of 3y would be 3 times dy dx. The x terms are just normal, minus 12x squared equals, the derivative of 5x would just be 5, the derivative of 1 would be 0. Now, do you remember what we would do to finish this problem? We would solve for dy dx. And I'm not going to take the time to do that, but that's how we would finish the problem. Okay? So, what we're going to have now is we are going to have two functions. We are going to have x and y as functions of t. So we're relating these two variables to t. We're relating x and y to a third variable, t. All right? And so we're going to have to use implicit differentiation. We're going to get an expression that's going to have x's and y's in it. Like, let's say that I had x squared minus y cubed minus 2x plus 7y squared minus 2 equals 0. Let's say that I have that expression, but we are relating it to a third variable, t. Well, if that's the case, I have to do both the x terms and the y terms like I do the y's normally. So when I do the derivative of x squared, it would be 2x dx dt. And this would be minus, what, 3y squared dy dt. Yeah, you do it like the y's, but you have to do it for the x's too, because we're relating it to a third variable. And this will all make sense in just a minute when we do a problem. Minus 2 dx dt plus 14y dy dt equals 0. Okay? Now what I want you to notice is that in this expression I have both a dx dt and a dy dt. Now, what we're going to see in our very first related rates problem is why that matters. We are going to have a problem where there is a ladder against a building. Okay? And let's think of this for a minute. Does the length, if a ladder is leaning against the building, let's say this is my building over here, if a ladder is leaning against a building and it starts sliding down the building, can you answer me this question? Does the length of the ladder ever change? No. Okay? The length of the ladder never changes, so we would call this T. And if this ladder is sliding down the building, then isn't the bottom going to be kind of kicking out this way? We would call that, and isn't this normally the x-axis? So we would call the rate at which it's sliding dx dt. And if you remember, isn't a derivative a rate of change anyway? An instantaneous rate of change. And the rate that it is sliding down the building this way would be dy dt. And those two things, like we saw up here, are called related rates. Because I've got a couple things changing, don't I? I have two different things changing. I have the ladder sliding away this way, and I have the ladder sliding down this way. And they're both related to the length of the ladder, T. Okay? So, let's look at the first example on your handout. A ladder 20 feet long, and if you're doing this from home and don't have the handout, I'll still try to give you the information. We have a ladder 20 feet long leaning against a building. Okay, so here's my building. I don't know how many stories tall it is. I'm just doing that so you know it's a building. The ladder is 20 feet tall. If the bottom of the ladder slides away from the building at a rate of 2 feet per second, how fast is the ladder sliding down the building? Okay, so now we're looking for how fast is this going? Okay, that is my question mark, and we're going to label these in just a minute. How fast is the ladder sliding down the building at the moment or when the top of the ladder is 12 feet above ground? So, we need to label some things here, all right? We are given that the ladder is sliding this way. That would be dx dt. Okay? But we don't know, we're trying to find this, which would be dy dt. All right? Don't I know the length of the ladder? Right? This is T. Okay? That's T. So, what we want to do is we want to start with the relationship. Don't I have a right triangle here? And don't I know a relationship about right triangles that relate the two legs to the hypotenuse? Pythagoras, right? If I call this x and I call this y, then I could say that x squared plus y squared equals 20 squared. Would everybody agree with that? Now, somebody mentioned, well, hey, we know what the y is, but when we are starting with this original equation, the only thing that we can plug in, all right, is the thing that is not changing. What is the one thing that is not changing? The length of the ladder, okay? So when you're setting up the equation, all right, when I'm setting this up, and you probably better write this down, note, when setting up the equation, only plug in, let's just say a number, a constant that does not change. A constant that does not change. And in this case, the only constant that is not changing is the length of the ladder. Okay? All of these other distances, okay, all of this and all of this are changing. So I can't plug in those numbers yet. I cannot plug in the 12 yet. We will in a minute. We'll use that in a minute. Now, because we're talking about a rate of change, it makes sense that we need to find the derivative. So, we're going to use that implicit differentiation with this that we just learned. The derivative of x squared would be 2x dx dt plus the derivative of y squared would be 2y dy dt equals the derivative of any constant is 0. All right? So, what are we trying to find? We are trying to find dy dt. But wait, I have some information. Don't I know what dx dt is? So I can put dx dt into this, and that will help a little bit. So I know that 2x times 2 plus 2y dy dt, already this thing looks a little bit better. And I do know that y is 12, right? I know that y is 12, so I could put that in. Well, we are at, the question did ask, what is happening at that instant? We're ready to start answering that question now. So I can put the 12 in for y times dy dt equals 0 plus 2 times all, I need to find the x value. How could I do that? The Pythagorean Theorem at that instant. At the instant that this took place, I have a little triangle that has a hypotenuse of 20 and a leg of 12. At that instant. Remember, everything with the derivative is instantaneous. So at the instant that we're talking about, the y coordinate is 12, and I can calculate the x coordinate. Okay? So if we do the Pythagorean theorem with that, okay, if I did x squared plus 12 squared equals 20 squared, and solved it, I'm just going to tell you what that is. It comes out to be 16. Now I know what x is. So I can put that 16 in right here. 16, this is times 2. And guess what? I now have all of the information in, and I can solve for dy dt. So this is going to be 32 times 2. This is going to be 64 plus 24 dy dt equals 0. And I'm out of room on this page. 64 plus 24 dy dt equals 0. Subtract 64 from both sides. 24 dy dt equals negative 64. Divide both sides by 24. And dy dt equals, if I divide both those by 8, don't I get negative 8/3? Which is negative 2 and 2/3 feet per second. Why is it negative? Very good, because the ladder is sliding down. The related rates problems help me identify if something is sliding down or going up. Okay, so that's important. Now, I want to give you something that's going to help you on the related rates problems before we do another one. and that is kind of a plan of action. Okay, and this is kind of what we did on this problem. How to tackle related rates. Related rates problems can be very fun because, like I said, they show us the real-world application of calculus. Number one, draw a picture. Okay, that's step number one. That's something nearly everybody can do or try to do. Draw a picture. Number two, we want to identify what do we know. What do we know? What do you think number three is? What are we trying to find? We want to know what are we trying to find. That's important. I need to have some direction for where I'm going with the problem. What am I trying to find? In the example that we just did, we did that. Didn't we say that we wanted to find a dy dt? Okay, so you need to know what are we trying to find. Number four, you need some type of formula or equation. Oh no, it won't always be the Pythagorean Theorem. You need some type of formula or equation. Number five, we're going to differentiate. And remember, we are doing that implicitly. Okay, differentiate. Remember, that means find the derivative. Number six is where we substitute and then solve. I think it has helped some of my calculus students in the past to have kind of a plan to follow on these problems. And so I think that will help. Let's look at example 2 on your handout. Example number 2. In this one, we have a hot air balloon that is rising. So hot air balloons always have pretty colors. So we've got this hot air balloon, and we've got this little dude in here saying hi. Okay. And the hot air balloon is rising. And it just so happens that we have a nice little right triangle again. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. So this is 500. You've got this dude over here with a rangefinder looking up. At the moment, the rangefinder's elevation angle is pi-fourths. So we have a moment, okay, we are concerned about the moment when theta equals pi-fourths. In our last problem, wasn't that like the moment when the ladder was 12 feet? Something similar on this problem. At that moment, the angle is increasing at the rate of 0.14 radians per minute. What do you think that is? Remember, we're in this, we've drawn a picture, now we're asking what do we know? So if it's telling me that the angle is increasing at a rate, what is that? This is changing. So this time I am told d theta dt is 0.14 radians per minute. Okay, this time we are relating an angle changing to one of the sides. Okay, now what does the question ask? How fast is the balloon rising at that moment? So the balloon is going up and we want to find dy dt. That's what I'm trying to find, is dy dt. Now, let's look at the information that I have here. I have two sides. I'm relating this side, I'm relating this side, and I'm relating an angle. Don't we know a trig expression that relates those?
Yep.
Opposite over adjacent looks like tangent. So look what I have. I have the tangent of theta equals, now isn't y changing? So I leave that as y, but is the 500 changing? No, the dude is standing at the same place the whole time. So I can go ahead and put in the 500. Remember, the only constants we can put in are the ones that don't change. And so, guess what? Look what step we're already on. We've done this, we've done this, we've done this, we've done this. Okay? So, now we need to find the derivative. Okay? The derivative of tangent is secant squared theta. But remember, we are doing this implicitly, so it is times d theta dt equals what?
If you do the chain, do you do chain on that?
Well,
The divide minus thingy? That's why
well, this is the same thing, isn't it, as, isn't this the same thing as 1/500th y? Right? So I could just say that that is 1/500th times dy dt. Okay? So look what we've got now. We've got our new formula that we have found the derivative of. Wasn't I given d theta dt?
plug in our
Okay? I was given d theta dt. All right? And I was given an angle for that instant, right? So I've got lots of information here, all right? And I'm trying to find dy dt. So I'm out of room here. Let me recopy this. Secant squared theta times d theta dt equals 1/500th dy dt. All right? So I know that at the instant that we're talking about, theta is pi/4. So I can make this the secant of pi/4, the quantity squared, times d theta dt, which we were told in the problem that is 0.14, equals 1/500th times dy dt. Now, wouldn't it make sense to go ahead and multiply both sides by 500? Right? Because we're going to be solving for dy dt. So if I multiply both sides by 500, 500 times this side, 500 times this side, get out the slasher, and I have got dy dt by itself. Now I've just got a little bit of algebra work. I have 500 times, what is secant? Isn't it 1 over something? It is 1 over the cosine of pi/4. That whole thing squared times 0.14.
and the bottom.
So now the cosine of pi/4, that's one of those values, that's like 45 degrees. This is 1 over radical 2 over 2, the quantity squared, times 500 times 0.14. Okay, and at this point, honestly, we're going to wind up, using our calculator a little bit anyway. But I'm just, however you finish this problem, if I were to square this, I would have 1 over 2/4, which is the same thing as, when I multiply by the reciprocal, as 2. So that's times 500. So that's 1,000 times 0.14, and I get 140. Now, again, I know maybe you may have used a calculator a little bit there. That's okay. That's just the way I went through it. 140 feet per minute is dy dt. Okay? Now, sometimes, if you look at example 3, let's just try to get example 3 set up. Sometimes you've got a couple things going on. At 1 o'clock p.m., ship A is 25 miles due south of ship B. So you've got a ship here, okay, and you've got a ship here. Okay, and it tells me that this is ship A, this is ship B. All right? And ship A is 25 miles due south. This is 25. If ship A is sailing west, it's going this way, at a rate of 16 miles per hour. And ship B is sailing south. Okay, let's slow down here a little bit. Ship A is sailing west at 16 miles per hour. That is a dx dt. Dx dt is 16. Ship B is sailing south. Okay, so this is dy dt is identified as 20. Find the rate at which the distance between the ships is changing. So the distance between the ships is the hypotenuse. Okay? So in this case, we've got this as z. Let's just call this x, y, and z. We want to find dz dt. Okay? Now, when I set up the Pythagorean theorem, x squared plus y squared equals z squared. Okay? Z is changing, so I have to leave it alone. But I've got a problem here because I've got 3 variables. Okay? So this y squared, isn't it going to be 25 minus y? Quantity squared. Okay? And so that is how we're going to get the problem started, and I will tell you that you're going to have to eliminate a variable later. We will finish this problem tomorrow.